Hey students, welcome back. This video is still a part of stoichiometry, but we also added titrations in as well because they kind of go hand in hand. So we're going to talk about solution stoichiometry, but again, that goes along with titration. So this is 4.6 titrations. If you need to read about it, there's some more information in section 5.7. Okay, so let's jump right in. In titrations, a titration is finding an unknown concentration using a known concentration. All right, so we basically do a chemical reaction with a known concentration or molarity of a substance to find an unknown concentration. All right, and when they reach that point is called the equivalence point, and this is where the moles are equal. And to figure out where that point is, we could either use a pH meter, all right, or we could use what is called an indicator, and an indicator changes color at different pHs, all right? The one that we use most often is phenolphthalein, which is what you see in the picture below. And so let's kind of talk about what's happening in a titration. So what we do is we start, most of the time this is like an acid and base reaction, but there are some redox titrations as well. But for our purposes for right now, this is an acid-base reaction. And we have maybe an acid in here, and we're adding a base to it. All right, and either one could be unknown and the other one could be known. All right, it doesn't matter. Then what we do is we drop a couple of drops of phenolphthalein. This pink stuff is called phenolphthalein, and phenolphthalein changes color at a range. This will also be a fun way to spell it. Phenolphthalein changes color in a range of 8 to 10. So what we're doing is as we add the base to the acid, right, we see this subtle color change. And what happens is when we reach our equivalence point, if we're looking on this at it in terms of like the pH is really, really low at first. So it's like going along like this. And then all of a sudden, when we reach our equivalence point right here, the pH jumps from really low to really high. And that's why we can use phenolphthalein, because this is quite a range. This will jump, like if you're using a pH meter, I've seen it jump from like 3 all the way to 10. All right, with like just one drop. And so what we have is, this is a burette. I think we've used burettes before, but if not, all right, when they are off, they are in this position. When they are on, this would be straight up and down. All right. But what we can see here is this would be our perfect equivalence point. All right, for phenolphthalein. That's where we have just a very faint pink color. All right, and it persists for 3 seconds. This would actually be way past our end point, and we would have like a pH of maybe 12 or 13, depending on the base we're using there. So what our goal is to get this very faint pink color, and we want it to persist for 3 seconds. All right, but for right now, we're going to actually go more into that when we cover our acids and bases a little bit later next semester. But for right now, this is kind of a good start for us. So we're really focused on the math portion. So if we take a peek at this, it says, what is the molarity of zinc chloride that forms when 25 grams of zinc completely reacts with CuCl2 according to the equation? Remember, there's our final volume. Remember that we can also use stoichiometry for molarity. So let's take a look at that here with this example. So we've got 25 grams. Make this just a little bit bigger. We've got 25 grams of zinc. All right. And our first step is to go from grams to moles. So we divide by the molar mass of zinc, 65.39 grams. And we'll put 1 mole of zinc up on top. All right. Now we do our multimole ratio. All right. And we know that 1 mole of zinc, this is from right here, goes to, we're looking for zinc chloride, so also 1 mole. So we say 1 mole of zinc chloride. All right. Now, at this point, we would be, if we did the calculation, we would be at moles of zinc chloride, right? And we know our final volume is 0.275. So according to our molarity equation, molarity equals moles over liters. If I just divide by liters here, 0.275 liters, all I did was convert that to liters, right? Then I would have my molarity, which is what it's looking for. All right, so we can just do this calculation, and notice how we did it all on the same little line. So we're going to take 25 and divide by 65.39 and then divide by 0.275, and this will tell us our molarity of our zinc chloride. And if we keep 3 sig figs, we're going to say 1.39 molar zinc chloride. So notice how we could do that, and that wasn't our titration, but we still do the same kind of premise, if you will. All right, so let's try an actual titration, which is this next one here. All right, here we go. The titration of 10 milliliters of HCl of unknown concentration. So we're going to be finding HCl's concentration. Requires 12.54 milliliters of NaOH. To reach the equivalence point, what is our concentration of HCl in molarity? So our first step of any stoichiometry problem is to write our balanced chemical equation. So we have HCl plus NaOH. This is a double displacement reaction. We also know that in an acid-base reaction, we get water. So water is one of our products. So we get HOH. This actually helps us balance it because we just see it taking places. We see our H and our Na kind of switching places here. So then Na will be chilling with Cl, and it's balanced. So it's all 1-to-1. So let's do this in terms of a stoichiometry problem. So now our next step is to go to moles. Well, to find moles using our molarity equation, we take molarity times liters. That will give us moles. So we're going to take 0.10 times our 0.01254 liters. Notice I just converted that to liters and we move it 3 places to the left. This will give me moles of NaOH, which is basically just going to move the decimal 1 place, right, to the left, right, and we're going to get 0.001254, and that's moles of NaOH. So we're already at moles, which is where we want to be. Now we're going to do our multimole ratio. Right, our multimole ratio, which is 1-to-1. We have 1 mole of NaOH, 1 mole of HCl. All right, and since we're at moles, we can divide by our liters, 0.01000, and that will tell us our molarity. So our molarity of our HCl, blow this up just a little bit, 0.125. And there you have it. Fairly simple. There you go. Good luck. See you on the next one.